Hi there. Welcome to another video tutorial session. In this video, we will be designing and constructing a solar tracker with weather station using Arduino. This project will be able to track the direction of the sun and also show us vital weather information like rainfall, humidity, atmospheric temperature, the sun irradiance and even atmospheric wind level. We will assembling the project design following a schematic diagram and also program it using the Arduino IDE. We can also remotely monitor the weather station sensors, using the IoT platform provided free by Zafron. We can see the atmospheric humidity, temperature, rainfall amount on the sensor, the luminous intensity or irradiance is measured and calculated by the LDRs in the project design. Stay tuned as we take you through all of these step by step. Please, before we continue, we would like you to take a moment to encourage small creators like me. Subscribe and share this video today. To get the complete list of the components and materials used for this project design, kindly visit the link in the description below. We have curated a complete list for you there and their uses too. Now, let us begin with the schematic diagram for this project design. The solar tracker with weather station project design is built around the Arduino Mega development board as shown in the circuit diagram. We connected the various sensors to the development board. Also the various actuators needed for the control of the solar panel that is mounted at the top of the robotic system. We are using 4 light-dependent resistors, LDR, to check and calculate the irradiance of the sun. These LDRs also help us determine which direction to turn the solar panel when the sun is moving with respect to its position. We use 2 servo motors for the horizontal and vertical rotations of the solar panel. Since the system design had a backup battery, we included a DC-DC buck converter to buck the voltage down to 5 volts. The digital humidity and temperature sensor's digital output pin was connected on a digital pin on the Arduino Mega board, whereas the rain sensor to detect the amount of rainfall was connected on an analog pin on the Arduino Mega board. We excluded a wind vane in this design though and made use of the irradiance calculations using the 4 LDR sensors on the top of the panel holder. To send the sensor readings to the IoT platform, we used the ESP8266 module which we programmed and gave internet access. You can read more on the explanation on the schematic diagram and its connection in the link in the description below. Now we proceed to coupling and assembling the components together to make the project design ready for programming and testing. First we begin with the various sensor connections according to the schematic diagram. We have saved time in this video and have already soldered the variboard and connected the switch too. Now, we are using a 3x6" plastic casing to house the Arduino development board and the header connectors for the actuators and the sensors. This process is usually messy, but if you know exactly what you are doing, it will be easy for you. After we successfully mounted the Arduino Mega Compact type on the female header pin soldered onto the variboard, we connected the rest of the sensors and the actuators. Also the backup battery system. This connections and wiring usually take some time, but eventually we finished it and proceeded to the cable management stage. We used some cable ties to wrap all the entangled wire mess in the 3x6-inch casing box. And it also helped us to use the cable ties to neatly arrange the wires and cable at other places too. Now, let us program the Arduino Mega development board. For this project design, we have reserved the Arduino code in the link in the description below. We have also included the explanation of the code in the blog post link. We wanted to make the modules in the project visible to the user, hence we used a transparent casing cover for the project casing. We can remove the seal here to reveal that. When we turn the device on, we can check the performance of the project casing by testing it in the nighttime or a place where is there a little light. We shine a torch onto the surface of the LDRs and see how the solar panel is being rotated according to the direction or movement of the torch light. Now, we notice that this design has a flaw, since the LDRs were mounted on the same plane as the solar panel. To solve this, we separated the LDRs and the solar panel. Now, the LDR sensors are mounted on a separate pole. It is fixed and it can detect which position the sun is setting to. We run one more test on this new position to see how the robotic panel is being displaced. As we can see now, the program has been calibrated for a more efficient performance. This is the indoor testing of the project design. And so far it is working exactly as we programmed it to be. Next, we move to the outdoor testing. We expect the project design to position or the servo motors to rotate the solar panel to face the direction of the sun. And when we turn this device on in outdoor settings, we can see immediately that the solar panel is rotated to be facing the direction of the sun. And when we block the sun rays by casting shadows on the LDRs on top of the sensor pole, the design also responded accordingly. This means that the project design itself is smart enough to know and follow the direction of the sun lights to ensure maximum harvest of the solar panel. Now, we can proceed to sending our weather station readings to the IoT platform on Zafron. On the Zafron IoT dashboard we can see the periodic readings of the sensors connected to sense and read the weather parameters. These reading will continuously update itself every minute. And that is what makes this project unique. You can monitor any of the weather parameters from anywhere in the world. And that is it for us on this project tutorial. We will like you to comment below if you have any questions or any idea on what project you want us to do next. Thank you for watching and see you on the next video.